Hey, I'm Oliver Jessup, and I'm building a lightsaber. This is the third episode in a series of videos where I talk about the process of making this lightsaber. The last episode, we talked about making all the mechanical components of the hilt. If you haven't seen that, you should go watch that. And in this episode, we're going to talk about doing all the electronic components, like all the PCBs and all of that. And I can tell you, this is going to be a long one. I started designing all the electronics by first putting together a few flowcharts to figure out what sensors and components I would use and how I would get them all to communicate. I went through a few revisions, starting with a Teensy 4.0, an Atani, or an ESP8266, but I ended up settling on an ESP32 as I had like all the functionality I needed. And so here's a flowchart of all the final components that I ended up settling on. The ESP would manage its battery by reading the fuel gauge and have the ability to completely disconnect its own power. The sensors for the lightsaber included the VL53L5CX time-of-flight distance sensors, the MPU 6050 gyroscope, and the built-in ESP32 capacitive touch sensors. The ESP would also play audio files that are stored on a SD card through an audio codec. A boost converter was also included so that it could power all the LEDs as well as the audio codec. On the subject of LEDs, for the blade of the lightsaber I used 2 strips of WS2812B LEDs, and these strips had a LED density of around 144 LEDs per meter, I believe, which is crazy overkill. And each of these LEDs can draw like up to 30 milliamps, given that they're full power, bright white. So crunching the numbers, I have 223 LEDs throughout this whole blade. And then if the blade is drawing the maximum power, full power, bright white, then that gives me a maximum current draw of 6.7 amps. And for this application, calling that a lot of power is a crazy understatement. But we'll cross that bridge when we get to it. These LED strips were stuck back to back and then wrapped with foam and then also wrapped with baking paper to diffuse the light. This mess of LEDs, foam, and baking paper was then shoved up a polycarbonate tube and then capped off at the end with a piece of CNC milled polycarbonate. I also put like a small LED at the bottom of the lightsaber that was connected to the rest of the blade so I could control it using the same code. But I put this LED there just to signal the status of the lightsaber to show whether it was charging or how much power was left in the battery. The next thing in the lightsaber to look at is the battery. Considering like the crazy power demands of the LED strips, I decided to go with one of those high current draw 18650 cell batteries. This thing is a lithium polymer battery which can deliver up to 20 amps of current, which is plenty of power for all of the LEDs. I had a custom battery holder printed as well out of resin so that the battery could be slid snugly into the bottom of the polycarbonate lightsaber blade. And this battery holder also had a little slot out of the side which allowed the wires for the LEDs to pass around the battery. This allowed the battery to fit in between the emitter portion of the lightsaber and like the open ribs of the lightsaber, which allowed me to save a whole lot of space since the battery was inside the actual blade of the lightsaber and not inside the like electronic housing section of the lightsaber. With the battery taken care of, the next thing to figure out is the power control. And this was probably like the hardest part of this lightsaber to me. Like there were so many problems this gave me, and like I had to figure out so much stuff to get this thing to work. The WS2812B LED strips that I use require a stable 5-volt like input voltage, but the problem is that the LiPo I'm using only outputs 3.7 volts. It might have actually been okay to run the LEDs from this 3.7 volts, but it just kind of wasn't really a risk I was willing to take. This meant that I would need a boost converter that could boost my 3.7 volts up to 5 volts while maintaining an output current of up to 7 amps. So after a lot of searching over the internet, I stumbled across this lovely thing, which can boost the voltages around my LiPo cell voltage up to 5 volts while maintaining an output current of up to 8 amps. When I first incorporated this chip into my design though, its output voltage began to break down at only 3 amps of output. So I spent the next month experimenting and testing like a bunch of different capacitors and like different values of capacitors and like different PCB designs. And I was just trying to squeeze as much performance out of this thing as possible. I ran so many tests on this thing and like put together so many flowcharts and spreadsheets characterizing the performance of this thing before I stumbled across like an optimal capacitor to use and an optimal PCB design. But besides the boost converter, there are also a few other power management components on this lightsaber. For one, there was the battery monitor, which could tell the ESP32 how much power was left in the LiPo. I also made like a small MOSFET logical circuit so that the ESP32 could completely cut off its own power if the voltage of the LiPo got too low. The circuit would still reconnect to power though when the power button was pressed. The lightsaber would have two power saving modes that it could use. The first was sleep mode, where the LEDs and audio codec were disconnected from power and the ESP32 was sleeping but could still be rewoken using an external interrupt. This was good because it meant that there was minimal power draw from the lightsaber when it was in this mode, but it also means that there's no boot delay between the lightsaber being turned on and its ignition. The other mode that the lightsaber could be in is straight up power off, no current draw at all. The lightsaber enters this mode when the battery is low or it hasn't been used in a long time. It does take some time to wake up from this mode though, which means that you have to wait a significant amount of time between turning the lightsaber on and its ignition. Anyway, that's enough about power. Let's talk about audio. The ESP32 would output digital I2S audio to a max 98.35.7, I think I got that right, audio codec, which could play audio directly to a speaker. This speaker was placed near the top end of the underframe so that audio could be like emitted directly from the center of the lightsaber. The audio would be stored as WAV files on an SD card so that they could be read by the ESP32. To be honest, the physical components for the audio were pretty simple and like not that complicated to wire up, but where it did get complicated was all the software and stuff, but I will go into that in the next video. I had a custom PCB made for all of these components by JLC PCB this time. I made sure to use components that were in the LCSC catalog so that these PCBs could be assembled for me. The main PCB board that I had made that contained the ESP32 and all its other components was a 4-layer double-sided PCB. I made sure to use extra thick traces for the insane power demand of the LEDs and the boost converter. I'm sure there's like many things wrong with this PCB design, and I'm sure there's many other people who could design it better, but hey, it works. After getting the PCB, I ran a bunch of tests on it and checked to see if everything was working. And after that, it was nearly time for integration. There's just one more thing to address before we talk about the integration of this lightsaber though, which is the thing that makes this lightsaber completely unique from any other lightsaber, which are the 4 proximity sensors around the emitter of the lightsaber hilt, which allows me to detect if and where a contact happens along the blade. I made a custom PCB for these 4 sensors, and I spent ages just trying to make this thing as small and as compact as possible. Here's one I had left over. It ended up being a single-sided 4-layer PCB that I had JLC PCB assemble for me. The I2C communication protocol that the proximity sensors used saved me here, as it allows the number of wires needed to communicate with each sensor to be minimized. The sensor board was sized so that it could slide over the polycarbonate blade and fit on top of the emitter rim. Also, here's 2 of the main boards that I had left over. You can see the ESP32 on both of them, as well as the USB-C connector that I use. And these are actually 2 different models. I believe this one is the older one. Yeah, I wanted to use a flexible cable to connect to the time of flight distance sensor board, but I ended up not being able to use that. I had to change to just using some thin copper wires, as I didn't really, like, it was just easier to solder them on instead of using another connector like this one on the time of flight sensor board, as it was like too big. And yeah, over here are the two MOSFETs that I use to control the whole board's own power, as well as switch on and off the power to the audio codecs and the LEDs individually. On this board as well, you can see all of this whole section here is the boost converter circuit that I use. And I had to spend a lot of time figuring out how to make this as small as possible, as well as like efficient and optimized as possible. With that covered, it's time for integration. Before I integrated this thing though, I spent some time putting together a checklist just to make sure that I was putting things together in order, because there's like so many moving parts. It took me like a few days to fully integrate this thing. And here's a photo of me with this lightsaber's gut spread across my dining room table. The hardest thing to get integrated was the connection between the time of flight sensor board and the main board of the lightsaber. I used 8 super thin enameled copper wires thread between the underframe and the blade of the lightsaber. I had to be like super careful with this part just to make sure I wasn't putting too much force on the wire that would cause it to like break or fray. I also had to take the thing apart and put it back together like so many times as well during the integration just to iron out a bunch of creases, but it did all end up working in the end. And so finally, here's the lightsaber fully integrated. With the integration of the lightsaber done, all that's left to do is program it, and I'll talk about that in the next episode, so stay tuned. If you want the schematics for like all the PCBs and things that I made for this lightsaber, as well as all like the mechanical components of the hilt, those are all available in my Patreon, the link for which is in the description. So with that, I'm Oliver Jessup. Thanks for watching.